In our study of refraction so far, we've seen some patterns in the direction that light bends and the angles when light passes from one material to another across a boundary between the two materials. So first, let's just review what we've seen when light travels from a material that has a lower index of refraction to a material that has a higher index of refraction. So for example, this could be something, this could be air and this could be water. So first, let's review some of the different light rays. So suppose a light ray comes in perpendicular to the surface or the boundary between these two materials. It's traveling along the normal. So if we were to draw the normal, it would be right on top of here. And that light ray has an incident angle of 0, and the refracted angle will also be 0. So that light ray will actually continue straight through without bending. Now suppose we have a non-zero angle of incidence. So I'm going to draw a light ray that hits the boundary at an angle. So to properly do this, I should use a protractor, but the normal would look something like this. And you always draw the normal at the point where the light ray is hitting the boundary. So anytime you have a light ray hitting the boundary, just draw a new normal at that point where the light ray hits the boundary. The angle between the incident light ray and the normal is the angle of incidence. And what we observed was that this light ray, when it goes from a material of lower index of refraction to a material of higher index of refraction, it does not go straight. What it actually does is it bends, and it bends towards the normal, so that that angle of refraction is smaller than the angle of incidence. And let's consider an even larger angle of incidence. And here I think I probably do need to use a protractor to get my normal looking like it's in the correct direction. So the normal is this direction, and here's the angle of incidence. So we have a larger angle of incidence than in this example, but once again the light ray is going to bend towards the normal. So instead of going in a straight line through that boundary, it is going to bend toward the normal. And using Snell's law, we could actually calculate these angles. Okay, so every time you're going to have a refracted angle that is smaller than the incident angle because it's bending toward the normal. Now let's consider what would happen if we had the light rays going the opposite direction. So this is, I'll keep the materials in the same orientation. So this is going to be our lower index of refraction material and our higher index of refraction material. So for example, you could think of air and water. And if we have a light ray now, we're going to approach the boundary from within the higher index of refraction material. So we're approaching the boundary from the opposite side. So here's a light ray that comes in along the normal. It has an incident angle of 0, so it's going to continue without bending. It'll have you could say it has a refracted angle of 0, but it really didn't bend. Now let's consider an incident angle that's not 0. So I'm going to draw the normal so we can see the incident angle more clearly. So marking my 90-degree point enables me to draw the normal. So this is my incident angle, and the incident angle is in the material that has the higher index of refraction. And we observed that when the light ray is incident in this material with the higher index of refraction, when it moves across the boundary into the material with the lower index of refraction, instead of going straight, it bends, but it doesn't bend towards the normal this time. It actually bends away from the normal. So it's going to have some kind of direction like this. You can calculate that angle using Snell's law. And just to review, Snell's law, I'll put it right here, is the index of refraction of the first material that the light is traveling in times the sine of the incident angle equals the index of refraction for the second material that the light's traveling in. So for this example, it would be air, times the sine of the refracted angle. So that's Snell's law. And if you had values for these materials for their indices of refraction, you could calculate these refracted angles. But now let's take a look at a larger incident angle. So let's make it, say, like this, and drawing the normal. Okay, so we have a larger incident angle now, and the angle of refraction is going to also be larger than it was before. Okay, so anytime you're going from the material of higher index of refraction to lower index of refraction, you can see that the refracted angle is larger than the incident angle because it's bending away. It's bending away from the normal. This would have been the straight line path. Instead of going straight, it bent away from the normal. Now, you can consider here that as this incident angle keeps getting larger, the refracted angle is going to keep getting larger. And there should be a point at which that refracted angle actually reaches 90 degrees. And it bends so far that instead of bending to here, it actually bends all the way along the boundary. So there must be an angle. I'm going to draw another normal here. There must be some incoming incident angle. Some incoming incident angle that will cause a refracted angle of 90 degrees, which means that that light ray is now traveling on the boundary. The special incident angle that will cause a refracted angle of 90 degrees, that special incident angle is called the critical angle. And we can symbolize it as theta c. But it's just another incident angle, it's just that it's the special incident angle that will produce a refracted angle of 90 degrees, where that refracted ray is going along the boundary. The reason this is such a special angle is because if you now try to send the light in at an angle larger than this, so let's draw one more over here. If you try to send a light ray in now at an angle that is larger than the critical angle, and I'm going to draw that over here. Here's an incident angle that is larger. Okay, you can see that this incident angle here is larger than this one. The refracted angle can't get any bigger than 90 degrees, so it's gotten to its maximum. And what happens now? For any incident angle that's bigger than the critical angle, the entire light ray reflects back inside this medium. And now you don't need Snell's law because you just use the law of reflection. It's going to reflect just like a perfect mirror. So once you're past the critical angle, you just need the law of reflection. 10, 20, 30, 40, 50, 60. Actually, I should make my light ray a little longer so that I can measure the angle more accurately. So 10, 20, 30, 40, 50, 60, exactly 60 degrees. So this incident angle is 60 degrees, which means that by the law of reflection, the reflected angle will also be 60 degrees. So it's going to be in this direction. Okay, now this only occurs when the light ray is incident in the material with the higher index of refraction. And the reason that is because that's the only time when the refracted ray is bending away from the normal. and can become larger than the incident angle and can become as big as 90 degrees. So the idea is this critical angle is this very special angle here. It's an incident angle that will cause a refracted angle of 90 degrees. Now, how would you solve problems to find that critical angle? Well, the book has sort of derived another formula for that, but I would prefer you just continue using Snell's law. You do not need another formula that only works in a special case. What we can do is just always remember this diagram right here, and we will use Snell's law to find the critical angle for this special situation. And let's go ahead and presume that we do have air and water. And so for air is going to be the N2, and N2 is index of refraction for air is 1, and water is N1. It's N1 because the light is first in that material, 1.33. So here's how we can find the critical angle. We say, okay, the light is coming in the water, so N1 is for the water. And we're looking for the incident angle. So we're looking for the incident angle that is the critical angle, a special incident angle. N2 is the index of refraction for the second medium that the light would be getting to, which is air, so that is 1. And now, what is the refracted angle when light comes in at the critical angle? Well, when light comes in at the critical angle, the whole definition of the critical angle is that it causes a refracted angle of 90 degrees. So you put in 90 degrees here. Okay? So to find the critical angle, for your incident angle you put in theta c, for your refracted angle you put in 90 degrees. And now get your calculator, and we can calculate this. So 1 times the sine of 90, you might already know that the sine of 90 is 1, equals 1. So I have 1.33 times the sine of the critical angle equals 1. Now I'm going to divide both sides by 1.33. So sine of the critical angle is 1 divided by 1.33, which is 0.7518797. Now to find the actual critical angle, we need to take the inverse sine. So the critical angle is the inverse sine of this whole thing. So on my calculator, I can do the inverse sine of the previous number, and I get that the critical angle is 48.8 degrees. So what does this mean? This means that if I shine light in the water towards the boundary with the air, at angles less than 48.8 degrees, it's going to refract out into the air, just as in these first two pictures. If I shine light at 48.8 degrees, the light will travel right along the boundary between the air and the water. If I shine light in at 49 degrees, 50 degrees, 60 degrees, 70 degrees, 80 degrees, any number that's bigger than the critical angle, the light is going to completely reflect back into that first medium. And this whole phenomena is called total internal reflection. And it'll occur, so this is total internal reflection right here, and it will occur whenever the incident angle is bigger than the critical angle, you will have total internal reflection. So this is kind of it's called critical because it's a turning point between when you get a refracted ray outside and when you get a reflected ray back inside the material.